Next, we're going to look at two very important tests and for convergence or divergence of a series. And especially this first one, the ratio test, is going to be very important when you are working with the next couple of sections on power series and Taylor series and Maclaurin series. So pay close attention to this because you are going to use it quite a bit. So if we let the sum of a sub n be in series with non-zero terms, the sum of a sub n converges absolutely when the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is less than 1. The series sum of a sub n diverges when that limit is greater than 1 or infinity. And if you get 1, it's inconclusive and you have to use another test. Now, this is different from the limit comparison test that we looked at a few sections ago, because in that one you were comparing two different series, an a sub n and a b sub n. Whereas this one, you're going to be comparing a sub n to the next term in the series. So you don't have to bring in a different series, you're just going to be looking at the same one, but you're going to be looking at the next term of it. So this is an example. It says determine the convergence or divergence of the sum from 0 to infinity of 3 to the nth power divided by n factorial. And powers and factorials are the prime example of when you would want to use this test. So a sub n is going to be 3 to the nth power divided by n factorial, whereas a sub n plus 1, we're just going to replace that n with an n plus 1. So I've got 3 to the n plus 1 divided by n plus 1 factorial. So now I'm going to take the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. So I'm going to plug in what I know. So that will be the absolute value of 3 to the n plus 1 power divided by n plus 1 factorial divided by 3 to the n divided by n factorial. And I'm going to do keep, change, flip. So we'll have 3 to the n plus 1 power divided by n plus 1 factorial times n factorial divided by 3 to the n power. Now what I want to do is reduce things as much as possible so that I can get something I can take a limit of. So we're going to use the properties of exponents and the properties of factorials to break this down into something that I can reduce. So I'm going to take that 3 to the n plus 1 power, and I'm going to write it as 3 to the n power times 3 to the first power, because that would give me 3 to the n plus 1. And I know that n plus 1 factorial is recursively defined, so I can take the top portion off of that stack and write it as n plus 1 times n factorial, effectively counting down to the n factorial. And if you don't remember how to do this, take a look at our section on these sequences that involved factorials. And then I'm just going to recopy a sub n. Okay, so now you see some stuff should start to cancel out. We can cancel out 3 to the nth power, and we can cancel out n factorial. And I'm now taking the limit as n approaches infinity of the absolute value of 3 over n plus 1. So this is a constant term over something that's approaching infinity, and this gives me 0. Now since I got a 0, and 0 is less than 1, we can say by the ratio test the sum from 0 to infinity of 3 to the nth power over n factorial converges. And in fact, if you look back at the test, it converges absolutely. Looking at the next example, I have 3 to the n minus 1 power, I have n squared, and I have 2 to the nth power. So that's going to be my a sub n. And a sub n plus 1 will be 3 to the n plus 1 minus 1 divided by n plus 1 squared and 2 to the n plus 1, or 3 to the nth power over n plus 1 squared, 2 to the n plus 1. So I'm going to take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And just to save from having to write an extra step, I'm going to go ahead and do the keep, change, flip part of this. So I'll have 3 to the nth power over n plus 1 squared times 2 to the n plus 1 times the flip of this one. So that'll be n squared 2 to the n over 3 to the n minus 1. Okay, so now I'm going to break this down into the pieces that will cancel. So I'll have the limit as n approaches infinity. We've got a 3 to the n plus 1, or n minus 1, and a 3 to the n. So we'll write that as 3 to the n minus 1 times 3, because if you add those together, you get 3 to the n. We'll have n plus 1 squared, and I'll break this one down to 2 to the n times 2, because those powers would add to give me n plus 1. And it'll cancel the 2 to the n. Now hopefully you've gotten everything in a form where things will cancel. So I can cancel 3 to the n minus 1. I can cancel 2 to the n. And it looks like that's all I can cancel right now. So I get the limit as n approaches infinity of the absolute value of 3n squared over 2 times, let's go ahead and square that out, n squared plus 2n plus 1. Which is the limit as n approaches infinity of the absolute value of 3n squared over 2n squared plus 4n plus 2. And whichever way you need to go about evaluating this limit, if you use L'Hopital's rule or if you just compare the powers, this gives me 3/2, which is greater than 1. Now, since we go back to our chart here, if you get something that's greater than 1 or infinity, then we say that the series diverges. So by the ratio test, the series diverges. Okay, let's look at the next one. Now, since we need an absolute value, I'm not going to worry about -1 to the nth power. I'm just going to look at the absolute value of a sub n, which will be the absolute value of the square root of n plus 2 divided by n minus 2. And the absolute value of a sub n plus 1, we're going to add 1 to the n's here, so that will be the absolute value of the square root of n plus 1 plus 2, n plus 3 in the square root. And n plus 1 minus 2 will give me n minus 1. So I'm going to take the limit as n approaches infinity of the absolute value of this one. So this will be our a sub n plus 1. Square root of n plus 3 divided by n minus 1. I'll do keep, change, flip on this one and get n minus 2 over the square root of n plus 2. Okay, so combining things that we can combine, I'm going to combine the two square roots. So we'll have the square root of n plus 3 over n plus 2 times n minus 2 over n minus 1. And then I'm going to observe that this limit exists because we have the same power. Even though it's under the square root, you know that you can move that to the outside. These have the same power here, so this limit exists. So let's just split this into two limits and multiply them. That's one of our properties of limits from way back in the day. So the square root of n plus 3 over n plus 2 times the limit as n approaches infinity of n minus 2 over n minus 1, all in absolute values. So this one, again, gives me 1 over 1. And this one gives me 1 over 1. So I get 1. If you look back at your ratio test, the test is inconclusive when the limit of the ratio is 1. So we can't use the ratio test here. It's completely inconclusive. So that means that we have to do something else. Now, anytime I see this -1 to the nth power, I want to try the alternating series test. So we're going to try that. And that might have been a better option to begin with, but hey, we're in the ratio test section, so why not? let's take the limit as n approaches infinity of just the a sub n portion, the square root of n plus 2 over n minus 2. And you could do this by whatever method you're comfortable with. You might want to try L'Hopital's rule, or you might want to plug in some values, but this thing will go to 0. And then next we want to show that it's decreasing. I don't know about you. With this one, with the square roots, I don't really like to compare terms as much. So I'm going to look at f of x being the square root of x plus 2 over x minus 2. And I would take the derivative of this and show that we get something that's decreasing. So I'm not going to work through all the details of it, but you would need to use the quotient rule, and you would get negative x over 2 square root of x plus 2 times x minus 2 squared. And for x's that are positive, which all of these would be because n is approaching infinity, this would be a negative value. So we can say that f of x is decreasing. And so by the alternating series test, that tells us that the sum from 0 to infinity of the square root of n plus 2 over n minus 2 converges. So in the end, we couldn't use the ratio test. We had to use the alternating series test for this problem. But just be prepared because it may come up where you try to use the ratio test and it's inconclusive. The other test in this section is called the root test. And the root test generally works under similar conditions to the ratio test. So the idea here is that instead of comparing the ratio of a sub n and a sub n plus 1, we're going to take the nth root of a sub n, the absolute value of a sub n. And if that nth root happens to be less than 1, then it converges absolutely. If that nth root is greater than 1 or infinity, it's going to diverge, and it's also inconclusive when you get a 1. So things that this typically works really well for are exponential functions of any type, or any type base, either an a or b base or an e base. So with this one, I'm going to do the root test. So I'm going to take the limit as n approaches infinity of the nth root of the absolute value of a sub n. So that will be the nth root of the absolute value of 3 to the nth power divided by e to the 3n. And the absolute value is really not required here because both of these are going to be positive. So this would be broken down into the nth root of 3 to the nth power divided by the nth root of e to the 3n power. And I'm going to write that nth root as 1 over n power because I'm a little more comfortable with that. So this gives me the limit as n approaches infinity of 3 to the first power, n times 1 over n, divided by e to the third power, because that would be 3n over n. And guys, this is a constant, so this is just 3 over e cubed. Now the question is it less than 1, or is it greater than 1, or is it equal to 1? Well, if you put this in your calculator, you get a decimal that looks like this, 0.1494, which is definitely less than 1. So by the root test, we can say that the sum from 1 to infinity of 3 to the nth power over e to the 3nth power converges absolutely.